Hello everyone. In this video, let us try to look into the next quality check parameter, that is the duty cycle. So let us first try to understand what duty cycle is. So duty cycle is, for example, let us take this clock signal. For example, we have the clock signal clock period of 1 nanosecond. So duty cycle usually says that for what amount of time out of 1 nanosecond, for what amount of time your clock pulse remains high and for what amount of time your clock pulse remains low. So that is calculated in terms of percentage. Let's look into over here. So for in this particular example, for 500 picoseconds of your clock period, the pulse remains high, and for the remaining 500 picoseconds the pulse remains low. So it's an equal distribution of the high pulse and low pulse. So we say this particular clock has got a 50-50% duty cycle, and the clock tree that we have built is expected to maintain this 50% duty cycle at this point and at this point as well. So that is what the duty cycle check is all about. Let's try to for example, now what we'll do is when we transmit this this particular signal along these buffers, and for example we get something like this. So in this case, if you measure the duty cycle, if you measure the time period for which your clock pulse was high and you measure the time period for which your clock pulse was low, if you see, it could be 58% and 42%. It might not be exactly 50-50%, and there are reasons for it, which we'll be explaining in the further videos. So let me try to give you one reason that could lead to this is because of these buffers that you're seeing. So there are kinds of buffers in this. There are two kinds of buffers. One is the regular buffers and one is the clock buffers. So usually in the clock path we prefer a special type of buffer, which we will be explaining in the upcoming videos. But this particular buffer which are being used in the clock path has got some special properties, and this kind of buffers are only used in the clock path, not in other data path, that is the path between launch flop to capture flop. These are special kind of buffers, and that require some extra space. So those buffers are primarily used to take care of this kind of scenarios where we get a duty cycle of where the duty cycle is expected to be 50-50, but we get something like 58%, 42%. A peculiar thing that you see over here is the rise time and the fall time. They are different. So that is the main reason of getting this kind of pulse rather than getting this kind of pulse, because over here if you see the rise time and the fall time, they're exactly the same, and that is primarily the reason that this particular pulse is maintaining 50-50% duty cycle. That is exactly the reason. But over here we are not getting that because of the behavior of the buffers, and there are some physical properties of the buffer that is leading to this. So we will be trying to understand those things in the duty cycle check. Let us try to explain, let us try to understand duty cycle with one more example. For example, over here you have got a 1 nanosecond clock period, out of which for 200 picoseconds the clock remains high, and for the remaining 800 picoseconds the clock remains low. In this case, we will say the duty cycle is 20-80. It's 20% and 80%, and this particular clock tree is expected to maintain 20-80% duty cycle at this point and at this point. But let's see what happens when it goes through when it goes through the clock path. What happens is this. So the clock pulse remains high for less than 20%, and it remains low for more than 80%. So something like this. It could be 15%, 85%, and this kind of behavior can be really disastrous for a circuit, because there are some critical circuits, there are some critical applications that actually work on rising edge and falling edge. As I gave a very good example in the previous video, it was the DDR, dual data rate memory. So that those kind of applications need to be operated on high pulse or the rising edge as well as the falling edge. So if you don't have, if we are not able to get this kind of behavior at this point, it will be very difficult to run those applications. These are quite important applications, and these are quite critical applications on a chip. These are very small blocks on a chip, but they need this kind of they need these kind of pulses. That's why duty cycle check it becomes a very primary and very important check whenever we try to build a clock tree. So after the duty cycle, the next CTS quality check parameter that we have is the latency check. So latency is once you try to move from point A to point B, the time required to move from point A to point B is called latency. In the VLSI world, it's very simple. If you want to move from point A to point B, what is the time required to move through that distance, and that the time required is referred to as latency. So in general, what we want, if you want to move to a friend's place, we want to move as fast as possible. Basically, we want the latency to be low. We can take this particular analogy. Same analogy also works in the chip world as well. You want to move from point A, for example, let's say this is your point A and this is your point B. This is your point A and this is your point B. So you want to move from clock to their respective endpoints as fast as possible. But in the process, it should be optimal. It should not be very fast. It should not be very slow. It should be an optimal way. So let us try to calculate the latency in this case. So let's say from clock to this particular launch flop clock endpoint, the latency is L1, and the value of L1 is like 3 buffer delays plus 1, 2, 3, 4 wire delays. So you have the latency L1 as marked in this particular slide. So it's 3 buffer delay plus 1, 2, 3, 4 buffer 4 plus 4 wire delays. Next, let us calculate the latency of the other section. So let us call it as L2, and the latency L2 is like 2 buffer delay and 1, 2, 3 wire delay. So this is the values of latency. Now we have to consider, there will be some specifications that will be given to us that will decide on what this latency numbers should be. That is one thing. And second thing, the advantages of having low latency. So let's say this is a hurdle race. Let's consider this is a hurdle race. This is your starting point and this is your end point. So, and these are your hurdles. This is your one. This particular buffer is the first hurdle. This particular buffer is the second hurdle. This particular buffer is the third hurdle. So in a hurdle race, if you start from here, from this point to this point, you move straight. Then if you see a hurdle over here, you have to take a jump over here, and then you have to move from this point till this point, and again you see a hurdle, you have to jump again. You move from this point till this point, again you see a hurdle, you again take a jump, and you finally reach over here. So in all these jumps, you see you lose an extra amount of energy that is directly related of why to have a low latency. So if you have a low latency, the number of buffers that it will be placing over here, that will be less. And even if the number of buffers that is getting placed over is less, you will save a lot of energy. So for example, assume that there are more than 3 buffers. Let's say there are 10 buffers in this place. So if you start from this point, you will get this first hurdle, you will take a jump. You'll get some more hurdles over, you will take a jump. You will take one more jump. So you will take roughly 10 jumps. So in this case you are taking 3 jumps, but in the other case where there will be 10 buffers in this path, you will be taking 10 jumps. So 10 jumps it means that you are losing 10x amount of energy. 3 jumps, which means you will be losing 3x amount of energy. So you see how it's directly related. So if you talk about 10 buffers and 3 buffers, the amount of energy that is saved looks very minimal. But imagine a circuit, imagine a chip which has millions of flops, and in today's traditional chip world, in sub 100 nanometers circuits, we do have millions of flops, and this clock has to go to all those millions of flops with a low latency. So assume if you save 10x amount of buffers on each of the million of flop clock points. So these are only two clock points. Like this, if you have millions of flops, so you have millions of clock endpoints. If you try to save 10 buffer, if you try to say, let's say 10 minus 3, 7 buffers in each of the clock path, imagine the amount of power, amount of energy that you are saving. So that is the that is how it directly impacts your latency. That is it, how it directly impacts your power. So latency, so this is the clear advantage of having low latency. Basically, we explained two advantages of having the low latency. One is you will be having less number of buffers. Second, power dissipation. So let us point it down one by one. So the first point that we have made over here is the latency should be very less, and the advantages of having a low latency, the clear advantage that you see is the less number of buffers. So if you have less number of buffers, it's always good, because the more the amount of buffers, the more the amount of energy it will consume, and that will lead to huge power dissipation. And since it's a clock path, it's the heaviest switching element on a chip. The clock switches at every regular intervals because it has to switch. It has a regular clock period. So the clock is the heavy. Basically, this is the network that consumes like 70% of your power on a chip. The data path are not continuously switching, but the clock path consumes like more than 70%. They consume 70% of the power on a chip. So if you try to control the number of buffers, if you try to provide optimal buffers on the clock path, that is good enough. That is a very good strategy to save power. So what we'll do is, since I'm running out of time, we'll talk more about latency and the advantages of having low latency and power dissipation in the next video. Thank you.